This is the video podcast for Chapter 20 of Field Methods in Hydrology on the topic of infiltration and its measurement. So infiltration occurs when water that's falling out of the sky or running off the land goes into the ground, into the soil, and it's basically just the change in the water content in the soil through time and depth as that water is moving down or percolating down because of gravity. Infiltration data is necessary for a variety of uses in society. Of course, in agriculture, could be of use in wetland science, ecological functioning. It's also used in hydrological modeling because the infiltration is an important process in that, so we have to have the parameters, validation, calibration data for that as well. Also, of course, when you're looking at infiltration, soil property is going to play a large role. So knowledge about soil texture and just in general as a part of soil science, then you'll also see infiltration measurement being relevant. Well, let's just start with what could you do? I mean, let's just play dumb, right? Well, you could take a ring, such as shown here, a cylinder basically, that's open on the bottom and the top. You could hammer that right into the ground. You could pour water in there and have a ruler, and you could just watch the water as it drains out and just see, okay, as it's draining. Now, the first problem with a simple experiment of infiltration is that as the water goes down, the head, as we could say, right, the pressure induced by the water hydrostatically on the ground is also going down because it's getting thinner and thinner and thinner as that water infiltrates. So it really wouldn't be a fair test. So a simple modification would be to not allow the water to go down, but to keep it at the same level. So at set intervals, you could basically add more water back in and keep it at the same level. So imagine that this is the diameter of a shoe, maybe 8 inches to 10 inches in diameter. You hammer it halfway into the ground, and then what you do is you pour the water in the first place, and you have to be careful not to mess up the ground too much when you introduce the water, but you also have to do it fast enough that you're having somewhat of an instantaneous beginning to infiltration. And then when the water goes down a certain interval, like let's say 1/8 of an inch, then one way to do this would be to have pre-measured what the volume of water is that corresponds to 1/8 of an inch change, and have a whole line of those lined up. So as soon as that 1/8 of an inch goes down, then you add in the first cup, and then when it goes down to that level again, add in the next cup, and so on. And so you could just mark the time at which each additional 1/8 of an inch depth of water, or the corresponding volume, is added into the ring. That's one way to do it. The other would just be to have water in a graduated cylinder and just pour water in to bring it back up, and then just look off, read on the side. It wouldn't be as precise because it depends on how accurate your graduated cylinder is and the time it takes to read that value while you're also watching what's happening on the ruler. So this would be a discrete measurement in time because you're waiting for 1/8 of an inch of change to happen before you add more water. But still, it's a reasonable approach to take, and this would be called a manual single ring infiltrometer method. So just think about infiltration, the change in the moisture content of the soil through time. So integrated through time and integrated through the depth to see what's the total amount of water that's infiltrated and what is the rate at which the water is infiltrated. A single ring infiltrometer can give you that information. If you want to get fancy, another way of making this even better would be to not have to manually pour the water in, but automate the process of keeping the water constant at the same head, and then even potentially automating the reading of how much water is added continuously through time. So this shows an experimental setup with a larger infiltrometer in the ground here, and then there's a valve that's put in here that is what's called a float valve. A float valve, imagine you have a pipe, and that pipe can open or close in the vertical. Well, what happens is you just have something that floats, like usually a plastic square that's empty in the middle, or plastic cube. And when that rises, then it closes the valve. As the water level goes down, then the valve begins to open, and even being open a little bit is going to allow water to go in. So the rate of water that's entering the infiltrometer will depend on how open the valve is. Now, if the rate of infiltration far exceeds the total flow rate of your setup, then of course you need to have a bigger pipe and a bigger water supply. So that floating valve is fed by a hose, which then goes to a larger reservoir that has more than enough water for what you need for the experiment. This could be like a 55-gallon drum of water or more, depending on what your needs are. Then there is a tube here. It's basically just like a stilling well off on the side. You just have a pipe that runs to a clear tube that's graduated with like a ruler on the side. And so you could then manually watch as that goes down. An even better way to do this would be to put a depth sensor, pressure transducer into the tank, and let it be level at the start of the experiment, record in 1 second intervals, and just let the water depth change through time be recorded, multiply that by the area of the cylinder of the water reservoir, or whatever the shape of the reservoir is, and then integrate that through time to get your volume of infiltrated water. So what's nice about this approach is, first, you're keeping the head in the infiltrometer constant, and then second, you're changing the measurement from having to like read, looking over on the side of the infiltrometer, to reading in the water reservoir, which is a lot easier way to go. And then one more step up from there would be something called the double ring infiltrometer. And what this addresses is the fact that when you have an infiltrometer, the water isn't just going to go straight down, but you also have a pressure gradient because you have a high head on the inside, and you actually have a negative pressure, or a matrix potential, remember, on the outside. And so water always flows from areas of high pressure to low pressure unless you're in some, earth scale flow. And so water would be moving outside of the ring, which isn't really, that's not infiltration, that's a different phenomenon. So the double ring infiltrometer solves that by creating a ring inside of a ring, and then we only measure the infiltration for the inner ring. We allow the outer ring to create like a donut of water that's infiltrating down, and at the same rate, at the same time, in the same way as the central bulb here. This thing in the middle is just a float with a ruler on it, and then that's suspended by this setup here with, and is shown in this photo, so that basically as water is infiltrating, then you can read that value. Now this is set up here as a falling head infiltration test, but it's also possible to set up a double ring infiltrometer with a constant head infiltration test, in which case you wouldn't need this floating valve at all, because you'd be reading the change in water level in the reservoir. Okay, so that's a basic idea of how to measure infiltration. You want to create a table that has time in the first column, and then the change of time. So it's just raw time. Okay, the first second, the 5th second, the 10th second, whatever, and then the change in time from reading to reading to reading. What is the water level? What does that water level then correspond to into the cumulative volumetric water that's gone in? And then from one reading to the next, the difference in water level that's taken place, which could be like the change through time, which would be, per that interval, that would be the infiltration rate. So here's some typical data just to show you. Here's an experiment that took place over more than 200 minutes on the x-axis. Now, the y-axis has numbers, but you don't see a y-axis label, and that's because the label is provided differently for each colored line. The green line with the squares goes down, so we start with a very high infiltration rate of 5 centimeters per hour, and then it quickly drops off, reaching a near asymptote by the time you get to 200 minutes. You can also then cumulate that and that gives you the cumulative infiltration function, which has units of centimeter compared to centimeters per hour for the infiltration rate. So this gives you the first hint that what we're going to need in terms of infiltration measurement are both the rate of infiltration and the cumulative infiltration. And I'll show you how we get both of those and how we use them a little bit in some models later on. The big challenge that my experience has been with infiltration experiments is that the nature of your experiment just totally hinges on the initial moisture content. So here on campus, we often run this field methods class in the winter time because a lot of other hydrological measurements just aren't possible unless you're in the winter. However, with infiltration tests, when you do that in the winter, the ground is already fairly wet. So there really isn't much, we're not like experiencing a dry soil condition and seeing all of this early phase of infiltration. We may only be in this last phase down here. And so you can see this in the left of like what an initially dry soil would yield in terms of an infiltration rate response compared to a wet one. And my experience is that it's not even this. I mean, it can almost just be perfectly flat because it's near saturation. So an infiltration test is best conducted when the soil is dry and you can see the full range, or near the full range of what that infiltration function is looking like and how it's behaving. Also, this just shows on the right that of course there are effects in terms of texture and soil cover. This is showing soil cover. So if you have heavily grazed soils where animals have tromped down on it quite a bit, then you're going to have a smaller infiltration capacity and a lower infiltration rate because the pores are going to be all mushed up, and there aren't going to be as many, and they won't be as large or as well connected. With good soil, either because it's been churned up by machinery or just from bioturbation on a hillside, you're going to have lots of pores of all sizes that are going to make infiltration rates significantly higher. And in terms of texture, as you can imagine, when you have large grains and they're all about the same size, then that's the case when you're going to get large pores that are also pretty well connected. So gravel soils have the highest infiltration rates, then sands, then silts, and finally clay. If you have organic matter, depending on the nature of the organic matter, but usually it's going to be like root fragments, twigs, and pieces of bark or charcoal. They're going to create heterogeneity in the soils, both in terms of size, spacing, porosity, and they're also going to be decaying through time, which is also going to enhance porosity. So in general, organic matter is going to improve infiltration compared to a pure inorganic clay sample. One of the things that we need to do in hydrology is to use infiltration in our hydrological models to take rainfall and turn it to runoff. So here's a graph that's from a classic hydrology textbook, and it shows that through time you have precipitation, which is shown by this top line, time on the x-axis here, and then some fraction of that is going to infiltrate, and that's shown by this dashed line. And then above that is the water that is ponding on the surface and is available to run off to then create erosion. So this is a classic thing, is like how much of that rainfall has infiltrated, and how does that change through time during a storm? Well, we need to have experiments that we can run to get at what this dashed line looks like. I mean, we can generally see it has some sort of exponential shape to it, but we need to fit the parameters to that function to characterize it. So this is an example of a field measurement approach that falls into the model calibration and testing scheme. So I'm going to show you three different functions increasing in complexity. The first two are empirical, and then the last one is analytical, and we'll have to work through its derivation. But in the first place, we can just say, well, when you look at the data, I mean, it sure looks like an exponential decay function. So why don't we just try to fit that and see what happens? By definition, from basic mathematics, you should know that an exponential function has this form, like y equals a coefficient times your independent variable raised to some power. Now, what are we going to use for infiltration? Are we going to use I? Are we going to use, in this case, Z? Other times people will use F. You know, we always have this problem with different variables of what letter to use. So let's not get too hung up on it, but in this case, recognize that capital Z is cumulative infiltration and little z is the infiltration rate. Just be careful, this is not Z in terms of an elevation Z like we had with velocity measurement. This is infiltration Z. Anyway, cumulative infiltration will grow through time while the infiltration rate will decline through time. So if we start off with an exponential growth function and then we take the derivative of it, remember you just taking the derivative means taking the power exponent here, move it down in front, and then do a minus 1 and you've taken the derivative. So these are the two functions. Some of the basic rules here, a has to be between 0 and 1. And as time goes into infinity, the shape of this function means that infiltration is going to go to 0. So the main advantage of this approach is it's very easy to understand, it's easy to calibrate. The main disadvantage is that we know the infiltration doesn't go to 0. So when this soil is fully saturated, if you think about it, what happens when you have saturated water that's subjected to the force of gravity? It's still going to flow. It's just then going to flow as saturated water, and that would be what we would call Darcy's law for groundwater flow. So it's going to go to a constant value or a value in proportional to the head, but if you have a constant head, then a constant rate of flux. So what I'm going to do now is I'm going to switch to an Excel spreadsheet to show you how this Kostiakov function would work. So imagine you did an experiment and just imagine like a double ring infiltrometer that's been set up. The first column is the start time. So we start the experiment, t is 0. Now we look at what happens in the first 2 minutes. The midpoint of those 2 minutes is a value of 1, so I'm going to use 1 to represent the infiltration in that first 2-minute bin. This is kind of like in the velocity experiment, how you had to put a width around each velocity and depth measurement. It's the same kind of idea. We're just discretizing time into different bins. So we've had a 2-minute interval, dt, represented by the value at 1 minute, and the amount of water that was observed to have been used in that time, dz, was 2. Okay, and this is in units of millimeters, I believe. So you have 2 millimeters of cumulative infiltration, and if we divide 2 by the change in time being 2, that would be 1 millimeter per minute of infiltration. So we could just be accumulating the data that would be taking place, and you can see here just the time intervals increase because the rate of infiltration is getting very slow, and then this shows how much water is accumulating, and so we can calculate the cumulative infiltration and the infiltration rate. The two graphs down here plot that. The graph on the left is the plot of the cumulative infiltration through time. It looks like it should be centered actually on the midpoint. I'm not sure why. Let's see, what's this one centered on? Yeah, that one's centered on the midpoint. Okay. Geez, well, this should be centered on the midpoint too. That would make more sense. That's going to change some things, but okay. Okay, so we have these two functions, and then you can see what we've done is we fit equations to those functions. And if we just zip back to PowerPoint for a second, you can remind yourself that if we do a least fit regression to this power function, we can solve for k and a. So for the cumulative infiltration, then that's giving us as values of 2.12, which I need to now fix. Sorry about that. 2.1235, that's our k value. And then our a value is 0.3568. Okay, save that. Now, we can do the same thing for the infiltration rate function. In this case, the coefficient is Ka, and the exponent is a minus 1. But interestingly, you can compare those values between the two fits, and you will see that they are different. And that's inevitable because you have a relatively sparse data with noise, and depending on how you fit it, then you get, it is sensitive. And so that shows one of the limitations of this kind of field experiment with sparse data. It'd be better to have a lot more data and then be able to fit it. So we can take the infiltration rate function here from this fit, and then we can solve for what the infiltration rate values are. We can take the cumulative function, which is now wrong, but apologize for that. We can fix those values, and you basically solve for that there. And then also we could do the integral. So if we start with the infiltration rate function and we integrate it, which I've done off on the side, and this spreadsheet is linked so you can download it on the same web page where you're watching this streaming video, then you can get the integral of that infiltration rate function and see what that is. And then it's possible to compare all of these functions and have it all going. So that shows the data side of an infiltration experiment using the Kostiakov function. If we now move on to the modified Kostiakov function, the idea here is to not end with a zero infiltration rate, but with a constant infiltration rate that should be equivalent to the saturated groundwater movement. Then we can have a function like this where all we've done is we've added this plus f of t. That's the cumulative function. For the infiltration rate function, then we have this f is just a constant. So it's the same integral and derivative approach. As t goes to infinity, then this term in the upper right is going to go to 0, and we'll be left with just that constant rate. I'd just like to point out to you, though, that if you take this cumulative function, if we move f of t over, then we can have an equation where we have y equals this power function. So if we want to solve for k and a for the modified Kostiakov function, we just have to independently get this data and then do the fit just like we did before. So I'll show you how that works in the Excel spreadsheet next. So if I click on the modified Kostiakov thing here, okay, well, of course, just straight off, in Excel, you can't plot a function of this form. So that's why we have to move things around. So we have I think this is the same data from the Kostiakov. Yeah, it's the same data, but now, and then what are we plotting it? It's all plotted based on stop. Don't know why. Sorry about that. I've used this spreadsheet for years, and I don't know why this has never come up, but okay. Anyway, I'll just fix this here. Always good to see professors make mistakes and see how that gets fixed, because then you're getting to see how you do this. And you can see I'm just taking the values off of the equation and shoving them up there. Okay, so we've got z, cumulative z, and these are just coming straight from the data. Cumulative infiltration rate. Now what I'm going to do is I'm going to make, okay, the first thing I'm going to do is I'm going to look at the infiltration rate data, and I'm going to see, well, what is this value that it's asymptoted to as the steady state rate? And I'm just going to pick that value of 0.03 as representing f. Once I've set f, then it's pretty easy to just say, okay, calculate, let's see, well, this should be on dt. No, it's at that time. That's fine. That's okay. So we're looking at the cumulative infiltration minus the steady state rate through time to the total time that we're up to at that moment, which is why the stop time is appropriate there. And we now make a fit. If I plot this z mod on the y-axis and t on the x-axis, then I can get the coefficient and the exponent that corresponds with over here, the coefficient k and the exponent a. Okay, so that would give me that, and then let's see this one. So similarly, I could plot the I can plot the infiltration rate data. That's all looking good. And again, if I bring the f value over to the other side, so it's z minus f, now I can solve for ka and a minus 1, just like we did for the regular Kostiakov function, and get those values here. And apart from the mistake that I had made here, this should be based on that 1.96 number. But in any case, then I can fit the functions and get the values for the functions. Okay, so this shows you for the two empirical functions how you would go about conducting an experiment using a single or double ring infiltrometer, holding at a constant head, getting the data, and then fitting the data to either Kostiakov or modified Kostiakov functions. Just note that there is a function called Phillips function, the special case where a equals 0.5. So of course with empirical equations, different people came up with different ways of doing it, and so it can be named after them. Now we get to the big one, the big cheese. And so this is going to get a little bit more complicated because we're going to do an analytical solution, and that means we're going to need a little calculus and a lot of patience, and we're going to do some exercise for your brain. So if you haven't yet, pause here, take a break, jump up and down, get some coffee, but relax, get ready for some math. Now, why do we have to do this? Because this is the main equation that you're going to need to use in many cases for being prepared in a hydrological model to predict infiltration and then go out in the field and get the data necessary to test that model. So this model is called the Green-Ampt Infiltration equation. The setup here, first I'm gonna have to skip around just the way this was best for me to make these slides. So the line in the middle here at the bottom of the word water is the ground surface. Above that, water is ponded some small amount, and that is water where the word water is, up to that thinner line. The line on the bottom is the location of what we can call the wetting front. And what this means is that imagine that infiltration occurs as a plug of water that's all just moving down. And where my thumbs are, so that my fingertips would be the ground surface, and where my thumbs are is the wetting front. And as infiltration occurs, that wetting front is going to be moving down. Okay, so but the interesting thing here is it's assuming that the transition from the background soil moisture to the saturated condition is instantaneous along that wetting front. It's just like a wall of water moving down through the ground. Now the way this is plotted, the bold arrows indicate a coordinate axis, where the vertical axis indicates depth. And in this case, although it's pointing down, this would be in the negative direction. The ground surface is given an elevation z equals 0. And here at the wetting front, the elevation z is zf at the wetting front. Now I've done something miserable for you, and it's not my fault. Please don't blame me. I'm just the messenger. But for this Green-Ampt derivation, z, we're back to how we usually think of z, which is elevation, not z from the infiltration from the other functions. But I had to give you the other functions as they are, and now we're here. So again, clear your mind, do a little dance, forget about everything I just told you, and focus on the Green-Ampt equation. So z is now elevation, and it's really arbitrary to decide what's going to be positive or negative values, but for this derivation, we're going to assume that up is positive and down is going to be a negative number. So here, zf is going to have a negative number in it, a number less than 0. Okay, so that's at the wetting front. So what this axis is showing us is the vertical axis is elevation, and the horizontal axis is going to be the moisture content of the soil, theta. Theta I is the initial moisture content before wetting took place, and it remains the moisture content in the area that water has not infiltrated into yet. Theta S is the saturated content associated with that texture of soil, and so the difference between those two, if you just think about it, like that difference is the water, the total water that has infiltrated in the available time that wetting front to reach that position. Okay, now let's forget about these equations for a moment, and let's just think about the setup here. H was the depth of ponding, so you can see that we have water ponded on the surface. H, that's like the head. So if we look, what is the head? Right at the ground, it's the weight of the water above it. And since we're at an elevation of 0, then there's no elevation head component of it. So it's just basically the head associated with that weight or pressure of water on top of it. What's that? P over gamma G, I think. P over rho G? No, P over gamma. Okay, and we can also consider that this weird pitchfork look thing, that's called psi. That's the Greek symbol psi, and it relates to the matrix potential, which you may remember from our Veda zone presentation, represents the suction that the water wants to put onto it. It's usually a negative number, but it equals the head, and in this case it's a positive value because we do have a positive pressure. So it's more of a push down rather than suction at the ground surface. At the wetting front, there is going to be a suction present there. We don't know what it is, but we're just going to call it psi F for the suction at the wetting front. Okay, now we're going to use Q, which is the flux rate from Darcy's law, to represent saturated groundwater flow. But now for infiltration, and I hope you had time to clear your head, pretend that we didn't go through the Kostiakov function and all that. We're going to use the letter F. F is going to be infiltration rate. And so F is going to be, little f is infiltration rate, and big F is going to be cumulative infiltration. Now we hit the other ones I've already shown you. Psi F, suction at the wetting front. It's going to be a negative number because matrix potential is a negative relative to atmospheric pressure. Theta I, initial moisture content before infiltration took place and further down below the wetting front. Theta S is the saturated moisture content. And then ZF is the position at the wetting front. And there's a note here, just again, I already mentioned this, but so much of this is about thinking through how you set up the experiment, the direction of the values, whether you're going to have the negative out front of your variable or implicitly it's a negative value. Basically, you just have to be consistent, and I'm not going to dwell on that any more than that. But if you were, this isn't a class where the main purpose is to do example after example of infiltration. But if you were to take that class, then you would be getting tons and tons of this. It's just my job is to remind you that you need to be mindful of your units and as you're playing with numbers. So what are some of the assumptions in this method? Well, first, we're going to assume that the wetting front advances at the same rate. So as it goes down, it's not moving faster. It's not like slow, 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 and then it's speeding up as it goes down. It's just going down at a nice constant rate. And there is a well-defined wetting front that we can treat as a step function. The volumetric water content remains constant above and below. So above it's saturated, below it's at the initial moisture content level. And also that the soil water suction or matrix potential immediately below the wetting front remains constant relative to that position of the wetting front. Okay, so the first thing we're going to do is recognize that at the ground surface, we're in a saturated condition because we have ponded water above us and saturated soil below us. So the infiltration rate is essentially the rate at which groundwater would be moving according to Darcy's law. So we can begin with Darcy's law, which if you don't remember, you could pause here and go back to the groundwater video podcast, It tells us that we have a saturated hydraulic conductivity and we have a gradient in hydraulic head, in which case that's a vertical gradient. DH is the head at location 2 versus the location at location 1, which is shown here. At location 1, it's the weight of water ponded above it. At location 2, it's the suction at the wetting front. That's the pressure that's being felt there. Plus the fact that we're now at a different elevation relative to the datum, which is a negative number to the position of the wetting front. So we've got psi F plus ZF, and we substitute that in, and we've got H. And then our Z2 and Z1, well, Z1 is just 0 because we've defined that by the datum that this ground surface is our origin in the vertical. And then Z2 is the position of the wetting front. So we can just put these numbers in, or the variables, and we have this infiltration rate, which is the same as the groundwater flux rate, is equal to this term on the right. Okay, now we're going to hold on to that, And we're going to come back to this idea that if you think about what infiltration is, like cumulative infiltration. Cumulative infiltration is the change in soil moisture that took place from time 1 to time 2 through the depth over which infiltration occurred. So we could take the saturated moisture content minus the initial content. That difference is the change in water. Multiply that by the thickness here, and that's the total amount of water that's been infiltrated. So that's shown mathematically here, a few slides down. F is cumulative infiltration, Z is that thickness, and then this is the change in moisture content. We can now rearrange that to isolate ZF. So ZF equals F over this change in moisture. And if we go back to Darcy's law, remember how we have ZF here? The first unpretty step of algebra, it's just algebra, but it's not very elegant. We're going to substitute that in here. So we take this ugly thing, we put it in, and here's Darcy's law. Q equals F, the little f, that's infiltration, is the same as this groundwater flux rate, which is the same as d capital F dt. And then here's Darcy's law. All I've done, if you compare the previous slide to this one, is I just changed ZF with this ratio and put that in. The next step I'm going to do is I'm just going to flip the denominator. I'm not going to move it. I'm just going to, here's the numerator. Okay, I'm circling around it, and I've just kept it. Here's the numerator, same thing. But instead of having it literally on top, I'm just moving to the side and flipping it over so that it just is more compact to see. Now what I'm going to do is I'm going to multiply the three functions here by, let's see, so first I'm going to look at this and I'm going to say, okay, well, H, this head, at the time of ponding, like when ponding first begins and we have saturated conditions, the amount of water that's ponded on the surface is really small. And it's pretty rare in an infiltration scenario, unless you're in the river or in a lake, to have a substantial height of water ponded on a natural ground surface. So because of that, we're going to treat H as negligible. So we're going to get rid of that. Now I'm going to take this term and I'm going to multiply it by each of the terms in the parentheses. You can see that if I multiply it by the term that's in the middle, it basically is just the inverse of it. So it's going to go to 1. And then we're going to have psi f times that thing there. So here it is in the red box, negative k psi f times theta s minus theta I over capital F plus 1. And we're just going to rearrange this. So what we have now is we have infiltration rate solved as a function of cumulative infiltration and these other parameters. I just want to rearrange that to get cumulative infiltration isolated. It's just algebra. Just take k and bring it under, so I have f over k. Now, the next thing I need to do is, see, with the 1 here, right, so the negative applies to both terms. So this is, the negative on the outside makes this a negative 1. So I add 1, so I have f over k plus 1, and that's shown here in this denominator. And then what I'm going to do is I'm going to multiply both sides by capital F to bring f over and get rid of it on this side. And then I'm going to, let's see, and then I'm going to divide both sides by the 1 plus f over k and bring that over here. And then that's going to be there. So it's just a simple rearranging. And now I've got capital F, cumulative infiltration, as a function of those parameters and infiltration rate. So the thing that's a little bit unsatisfying about this is that when you look at this function in the red box, there's no time here. Remember with the Kostiakov and modified Kostiakov equations that we were getting infiltration through time. I mean, doesn't this seem a little stupid? Like basically I'm just saying, well, if I know cumulative infiltration, I can just calculate the infiltration rate. Where's time? Well, the answer is that time is in the definition of f, little f. So little f equals df dt. So if I now make a substitution, then I can separate and integrate by parts. And this is where the calculus comes into play. Before I move forward, I would like to iterate, this is a field methods class. It's not a class where I'm here to test you on your skills in calculus. I can encourage you to learn calculus to understand the fundamentals of hydrology. If this was a course specifically on infiltration, then I would expect you to understand this derivation. However, my expectation, this is sort of like a capstone course. It's intended that you've already taken a variety of hydrology courses, which is why the vast majority of students in the class are hydrology majors, and many of you have already taken soil physics and other courses. So I will show you the steps in the infiltration, but I won't dwell on them, and they certainly won't be on the test. Okay, so we separate this by part, and notice that we, when we do this separation, it's easy to have the df/dt here, or actually, I'm sorry, that would be here, but we still have a capital F on the inside, so that's still there. So now we have this pretty ugly looking integral, 1 over this mass equals this nice simple thing. I mean, obviously on the right side is just going to integrate to time, so that's easy because Ks is a constant independent of F and T. So now what we have to do is let's see, so the next step is, it looks like we've just simplified this function because it's 1 over all this, so we've just flipped it around. And now what we have to do is recognize that whenever you have a denominator that's this ugly, then you have to use a substitution approach in integral. So we define the substitution variable u is equal to all this stuff. That puts us to u on the bottom. We then have to write f in terms of u, and that puts this on the top. We can now go ahead and do that integration, like the integral of 1 over u is ln u. So that's where that comes from there, and we're good on this side. And then you're going to integrate this through time. So the time goes from 0 to the total time of infiltration that's been taking place up to there, and we have now all this stuff because now I've gone from u back to the regular variables. And then we just have to do all the algebra of that integrating through time. And then in the end, we end up with a function shown in red. Do I expect you to memorize this function in the lower left? Oh, it would be fun to just say yes, but the answer is no. I'm not going to expect you to memorize it. However, I will expect you to understand, and for some of you that may mean memorize, the functionality of this. So for example, if you have a higher initial moisture content, what does that do to infiltration rate and cumulative infiltration and time of ponding, for example, according to the Green-Ampt method? So things like that. I would probably just put this equation on the exam, but again, this is a field methods class. That's not the point here. The point is going to be to ask questions about the infiltration experiments themselves. So what this allows us to do now is we have a time, we have cumulative infiltration, and of course what you'd like to do is you'd like to solve for infiltration as a function of time, but you can see there's no way that you can take the right side and isolate F. So the way that we make this practical, well, okay, I'll come back to that. The way we make this practical is you just go in Excel, you create a first column with a variety of F values, and then in the second column, you solve for T using that equation. So you solve it backwards, basically. For different cumulative infiltrations, what time must have taken to get there. And then in the third column, you solve for little f for each value of big F. And then you can plot each of those as a function of time. I just want to note that we can also rewrite those functions with all positive values. So here we would be providing the matrix potential not as like negative 0.5 bars or something like that, but as just the positive value without that negative sign. So everything would have positive values. Okay, so how does this work in practice? If I go back to the Excel spreadsheet, I can now click on the Green-Ampt. What I have here, I have this solved both using positive and negative numbers, but let's just stay with the positive values. Okay, and so what we have here, let's see, okay, well this is all the same. I mean, oh yeah, 1.97. Everything here is the same, just looking at the units differently. At the top are the equations for the Green-Ampt equation. So what I've done here is I started on the left and I have put all of the values for infiltration in the first column. Then I've solved for T. If you look here, like T, I've put the function in and just getting, for the values for saturated hydraulic conductivity, suction at the wetting front, initial and final soil moisture. No, wait, sorry. In this case, phi is the saturated moisture content, theta is the initial moisture content, and SF is the suction at the wetting front. So I've put those values in, I get time, and then I can similarly, for those same values of F, solve for little f, and I get those values, and now I can make a plot of infiltration rate through time, and I can make a plot of cumulative infiltration through time, and have those functions. You can see that with the Green-Ampt function, we have a much more abrupt drop in infiltration rate than we did compared to Kostiakov function. It's a very sharp drop. So how you do this in practice is you would again, well, you wouldn't be using the field experiment to fit those things, but you could try to use this to back solve for individual values like K or psi f or whatever. But anyway, that's how you implement that function. There are a few other wrinkles to this whole thing. One of the things you might want to know is, what is the time and cumulative infiltration at the instant that the ground experiences ponding to begin? We can do that by recognizing that initially when you have a dry soil, the rate of infiltration should equal the rate of rainfall intensity, because the ground should be able to absorb all of that water since it's dry. Okay, unless it's a certain kind of soil where the water literally is blocked from infiltrating, like it's concrete or something like that, it should be able to absorb all of that. So if the infiltration rate is less than the saturated hydraulic conductivity as shown in the bottom, then infiltration is going to occur at the rate of the rainfall intensity. And so as long as that's the case, like, before you reach saturated levels, then you're just going to be absorbing that. The ground is like a sponge, it's going to be taking that in. When you get to the point where the rate of infiltration is greater than that capacity to absorb it at that rate, then initially it will be taking in the water, but it will also lead towards ponding. So initially you'll be going at an infiltration rate equal to the rainfall rate, but then once ponding occurs, then that's going to change. And so the time of ponding equals the cumulative infiltration divided by the rainfall rate. And so you can solve for these things together by taking the rainfall rate, putting it in to this equation where you know all these other values, solve for the cumulative infiltration amount, and then put those two values in and solve for the time of saturation. I think S here is like saturation. And this just shows, like imagine you have a vertical column of soil, you have infiltration occurring. The change in moisture content is going to be a gradient. Here, the y-axis is elevation. The x-axis is not the space, not like across the soil surface, but it's the difference in moisture content from the saturated condition to the initial condition. And so you have this infiltration front, which is being simplified into a step wetting front function. And so that's going to be moving down through time. And this will be, first you're going to have to achieve ponding. So how much water has infiltrated before ponding occurs? Once ponding occurs, then the rest of the water is occurring under a ponded condition. So let's look at a sample calculation. So in this case, I'm going to give you the properties that saturated hydraulic conductivity is about 2 centimeters per hour. Initial moisture content is 31.8%. Final content is 51.8%. And a rainfall rate of 7.88 centimeters per hour, suction of the wetting front of 9.37 centimeters. These are all relatively high values, but they're not out of the realm of possibility, I suppose. So we can start off with putting the values into the functions, just like we said, solve for cumulative infiltration of 0.625 centimeters, and then we can put that into the time and find out that it takes 284 seconds to get to that point. So in terms of a practical thing, once you just understand the equations that are there, those equations, and yes, you can look them up in a book, and then be able to apply them. It's just if you get into the realm of irrigation, and of course irrigation plays an important role, as we've seen like in river restoration when you have a riparian zone, and often that has to be irrigated in the early years if you're in the western U.S. or other semi-arid to arid climates. Then this kind of information is something you'll probably just come to memorize and have at your fingertips. How do you get the values for different parameters? Okay, well, if you think about the function that's shown here, theta I, the initial moisture content, that's pretty easy. You could use the gravimetric method, take a sample, you could take a core, down to the first meter and just see what is that initial moisture content through depth. Take the average value. Saturated content would be done by doing an infiltration experiment. When you reach steady state, take a gravimetric sample and see what that saturated content is there. That all comes back to the methods from the Vado zone that I already talked about. Suction at the wetting front, that's tricky. In theory, you could put a tensiometer in the ground in the middle of your infiltrometer, and you would begin letting it equilibrate with the background suction for the initial moisture content. As the wetting front goes by, and if you're recording that data through time, you should see the transition between the initial moisture content and the final moisture content, and so you could try to estimate that suction at the wetting front from that progression. This also shows the ability to estimate it on the basis of texture, and same thing for hydraulic conductivity. You could take a sample, do a Darcy's law experiment on it, and get hydraulic conductivity, or you could take a value from a texture table like this, as a first estimation. Unsaturated hydraulic conductivity varies quite a bit on the basis of moisture content, and so this is basically similar to the topic we talked about in the Vado zone, the relationship between the matrix potential and moisture content, what we call that characteristic curve. Of course, if you have different matrix potentials, then water is going to be flowing at a different rate in response to that. So you have different unsaturated hydraulic conductivities with moisture. And then it also varies as a function of texture. And you can see that these are over orders of magnitude difference. Another really important caution about this trying to do infiltration experiments is that when you're looking at natural landscapes are just, they're alive, right? I mean, there's all kinds of worms and ants and other insects, as well as mammals burrowing into the grounds, roots that have pushed through and created pores. There's also can be swelling and shrinking of soils, freezing and thawing and wetting and drying. All of these processes create what we call macropores that create preferential flow paths, differential flow speeds, that can make it much more complicated. So I'll give you an example. We were doing an infiltration experiment in this class many years ago where we basically had a steep hillside. It was a long Puda Creek along the bank there. So we had a pretty steep, large single ring infiltrometer in a diamond configuration so that all the water was funneling down the hill to a point. And we basically had two 100-gallon reservoirs, and we decided to do the infiltration by a water balance method. So not a ponded infiltration experiment, but more of a sprinkler experiment. For each reservoir, we had a hose that went to a sprinkling head, and then we had two students, one on either side of the diamond, running their hand with the sprinkler back and forth to create a relatively even distribution of infiltration. And then we had a tipping bucket gauge at the tip to try to measure surface runoff. So the difference between water applied and runoff would be infiltration. Well, we were just pouring water on there. I mean, it was just like raining cats and dogs, and nothing was coming through the tipping bucket. We went through both of those tanks, and then all of a sudden, farther down the hill, like someone starts yelling. This giant spout of water shoots up in the air. The whole thing just drains out, and like the spout just, like all the water is just gone. So like the whole hill was like some underground reservoir. Nothing came out through the tipping bucket gauge, and then suddenly like some macropore exploded and just blew out, and all the water just came out of the hill. So, here we were like trying to do our infiltration sort of thing, and we're getting nothing. So it's pretty amazing when you think about natural soils and how they are can be very highly porous. The key is that there's a very different setting in an agriculture or urban context where soils are heavily compacted, and an infiltration test is going to yield a fairly simple result compared to what happens with a natural soil. So if you try to go to Australia and go to tropical rainforests and do an infiltration test, you'll find that it's quite a bit more difficult. And just as one last note, in this class we used to do an infiltration experiment. We used to do them on the quad where all the students are sitting out and eating lunch, and over many years they've compacted down the grass and so forth. And we basically just found that there's very, very little infiltration that takes place there on the quad. But it was still fun to do that and use our class to inform things on campus. So in summary, what I've tried to present in this video podcast is the basic methods of doing an infiltration experiment in terms of single ring and double ring infiltrometers. They can be as small as a coffee can with the bottom cut out, or as big as like a 2 meter by 2 meter diamond or square. It really helps if you have a constant head infiltration test, but there are also methods and equations for doing a falling head test. And once you have that rate information, what you typically want to do is fit an empirical function like the Kostiakov or modified Kostiakov functions, or take the Green-Ampt method and be using that field data to calibrate the parameters, which could be the suction at the wetting front, for example, or saturated hydraulic conductivity. And then you could be using that in the form of Richard's equation or something else in a numerical model for rainfall to runoff.